have here a way to block, right? You have a string number coming in, you form a vector representation. The vector coming out. And how do we reconstruct? You just deblock, right? Interlace. So we have something by 2. That. If I connect these two lines together, and I know that if I block and deblock, it's perfect. Y of n is x of n minus 1. It's 1 delay. Right? Remember this one? Okay. And furthermore, what we have done last time is we said, okay, this can be identity. What if I introduce 2 blocks? And they are inverse of each other. And in particular, we're using an orthogonal block, right? We use 1, 1, 1 minus 1 equal minus 2, and so on. We use this choice to get the power filters. Right? You can show that they are orthogonal, so the transpose will be the inverse. Okay, and this is a power system. It's an orthogonal system. And you can show that if you're building basic building blocks, it's orthogonal. Then you have orthogonal filter bank, orthogonal Wavelets, and so forth. Okay, I won't have time to prove it. But the basic idea is that if the system inside here is orthogonal, then you have orthogonal transformation. Now compare this form to this form. What's the difference? They look very, very similar, right? HP is matrix, FP is matrix. In this case, they are both constantly. Okay? But in general, if the product, right, if I can find FP of 3 and the corresponding inverse, FP of 3, if it is zeta minus L, let me use L hat, okay? It's a different L. Then you can show that if this is zeta minus L hat, I can pull it outside and we come to this structure, the lazy filter structure. Okay, so that would be the PR condition. So PR, right. The reason why, okay, the first reason why we use polyphase is that it allows us to build multi-rate system efficiently. So if you look at any multi-rate system in the world, the system will convert from one rate to another rate. If you build a system that works in both the US, let's say an audio system, both work in the US and in Asia, the same rate are different, right? One is 44.1, one is 48.4. So there are different rates. How do you change the rate? You have to have some kind of multi-rate system in there. If you open up any of the systems that you divide, there'll be a box inside that convert rates. Okay? If you look at a GSM network, cable network, there'll be also a rate changing in there. Because for ADSL, you're combining multiple low bandwidth to a high bandwidth, and so on. Okay, so open up any practical system, you will see boxes that have rate changing capability. And we never implement it like this. It is highly inefficient. Right? For 2 channels, you double the complexity because filtering at high rate and we throw away information. It's not good. Imagine that you have 32 channels. It's very, very wasteful to filter at high rate and throw away 31 samples. Right? So the much more efficient way, the first use of polyphase is to implement multi-rate system efficiently. That's what we showed yesterday. Okay? The second use of polyphase is to allow us to have another way to represent filter banks. Now, filter banks, you will see it also in cable network, representative cable system, ADSL, and so on and so forth. So I have both the analysis, decomposition, and reconstruction. Any cascade like that would need a filter bank. Okay? And a filter bank is a cascade of this decimation and interpolation. So we can show that using filter bank, polyphase filter bank. I can represent this operation efficiently, right? Instead of filtering at high rate and throwaway information, I first block the input and I'm filtering it at a low rate. All right? Why is low rate? Because we only have to filtering at every 2 samples coming in. Right? In the other side, when you do reconstruction, we don't want to insert 0 in the sample, increase your memory, and then filtering. That's not efficient. First, we want to filtering at low rate, and then just interlace. This operation is free, right? This is basically indexing problem, right? There's no operation in here. This is indexing. Okay, so this comes for free, that comes for free, and here we implement at a low rate, and here at a low rate. That's the first use of polyphase in filter bank, to get an efficient way to implement a filter bank. Right? The second use is that if we can design a 2 system, a 2 polyphase matrix, such that they inverse each other, then you get perfect reconstruction. Okay, so what's the next question you should ask me? In the book, this is called condition. Okay, or say compound. All right. So I'm going to start with one example we know before. Tell me a simpler system that's a solver that you know before. Okay. So we're going to draw again half filter bank. And if you recall, this is 1, 1, 1 minus 1, 1, 1, 1 minus 1. So I'm going to draw again the polyphase form. One minus 1, and equal to normalize the norm to 1. 1. And we know that the filter here is 1 plus the inverse, 1 minus the inverse, scaled by 1 over square root of 2. Right? Similar. Okay? How do I generalize this? So I start with a length, so this have length 2, right? Length 2. Length 2 meaning that the filter H naught have 2 lengths, okay? 1 and 1, and so on. How do I have a longer length?